welcome. This is going to look at section 25.7, really looking at how your kidneys regulate how concentrated your urine is and how much urine you're making. When you're dehydrated, right, you don't pee a lot. Your urine is very, very dark. It's very concentrated. It's what we call hyperosmotic. Because it has a higher than normal concentration. When you're very well hydrated, you can have kind of copious amounts of kind of pale yellow urine because your body has like an excess of water and it doesn't need to keep it. And being able to kind of regulate and change the concentration and the amount of urine that your kidneys make helps us to hang on to our water when we in fact need to hang on to it. So it's actually the loops of Henle, particularly the loops of Henle that are in those juxtamedullary nephrons, the ones that have the really, really long loops that descend down into the medulla, that are responsible for our kidney's ability to change the concentration and volume of the urine that we make. We have two sets of fluid flows. We have the fluid flow of the filtrate through the tubule, and then we have the fluid flow of the blood in the Vasorecta, and in both instances, because of the kind of little hairpin turn in the loop, we get these kind of fluid flows that are in opposing directions, right? The fluid goes down the descending limb, the filtrate, and then up the ascending limb. And those limbs are really close to each other, so they can influence each other. And then the same thing with the Vasorecta. You have blood flowing kind of down the Vasorecta and then up the Vasorecta, and again, the kind of limbs, as it were, quote unquote, of the Vasorecta are sitting pretty close to each other and can influence each other. And so the purpose of these juxtamedullary nephrons and these big long loops of Henle creates what we call an osmotic gradient in the medulla of the kidneys. The kind of solute concentration in the cortex is about 300 milliosmoles. That's the unit that we use. But at the bottom of the medulla, it's about 1200 milliosmoles. And so we have this gradient in the kind of interstitial fluid of the medulla that allows particularly your collecting ducts to regulate how much water gets reabsorbed by the collecting ducts, which then varies the concentration of the urine and helps us regulate our blood volume. So there are kind of three parts to this. There's what we call the countercurrent multiplier. This is that filtrate flow through the nephron loop. That's what actually creates the gradient, as we're going to discuss here in just a second. Then there's what we call the countercurrent exchanger. This is the blood flow through the Vasorecta that keeps the gradient, preserves it, doesn't muck it up. And then the collecting ducts use that gradient and utilize it to vary the osmolality, or the concentration of our urine. So let's look at what I'm talking about here. So here we are in the interstitial fluid in the kidney. Here's our cortex, here's the medulla. You can see much lower concentration in the cortex than we are kind of deeper down here in the medulla. The juxtamedullary nephrons have these very, very, very long loops of Henle, not Henry, ha ha ha, and there are countercurrent multipliers. Countercurrent because the filtrate flows in opposite directions. It flows down here, but up here. That's what's actually responsible for making this gradient through the exchange of sodium and chlorine and water, as we're going to see here in just a second. That allows the concentration of the interstitial fluid to be multiplied from 300 to 1200. The Vasorecta is the countercurrent exchanger. Again, countercurrent because the fluid, the blood, flows down and then up with a pretty equal amount of exchange of salt and water. So it basically doesn't undo the multiplication that was done up here. And then the collecting ducts use and utilize this gradient to change the osmolality, the concentration of our urine. So let's look at the multiplier first. We are talking about the filtrate flow in the ascending and descending limbs of the loops of Henle. The different limbs have different permeabilities. Sodium, in particular, sodium chloride, is actively transported out of the ascending limb and that into the interstitial fluid, and that does some weird funky things with how the water flows, as we'll see here in just a second. Now keep in mind that the two limbs of the loop of Henle are not in direct contact with each other. They're not touching, but they're close enough that as the ascending limb does one thing, it can influence how the descending limb does another thing, and how both of them exchange water and solutes with the surrounding interstitial fluid. Because they're close enough to each other, they can affect each other and how each limb exchanges things with the interstitial fluid. So they have different permeabilities. The ascending limb, that's the second half, is impermeable to water, but permeable to solutes, particularly sodium and chlorine. So sodium and chlorine get actively reabsorbed out of the filtrate and into the interstitial fluid of the kidney. The descending limb is permeable to water, but not permeable to solutes. So water moves out of the descending limb into that higher interstitial fluid. And so we get this really, really salty interstitial fluid that kind of gets multiplied the further along we go in the loop. So this is essentially what happens, right? The sodium gets absorbed out of the filtrate into the interstitial fluid by the ascending limb. That causes more water to diffuse out of the descending limb, kind of following the higher salt concentration. But as the water goes out, the filtrate gets even saltier. That salty filtrate is chock full of sodium and chlorine that can be actively transported out by the ascending limb. Because remember, the fluid moves through the descending limb first. So our filtrate loses water and becomes saltier, and then that salt is then pumped out and back into the body to create this gradient. We'll look at the figure because the figure I think helps. Let's just look again at the way the fluid flows. The filtrate moves down the descending limb and up the ascending limb. So as the filtrate flows down the descending limb, it loses water, and that's what you see going on here, losing this water. And so if we look at our concentration, as the water moves out, the concentration of the filtrate gets deeper, and as we move deeper into the medulla, the concentration of the filtrate gets saltier and saltier. Well, as the filtrate continues to move now up the ascending limb, the sodium gets actively reabsorbed into the interstitial fluid, which then drives the water out into the interstitial fluid. And so sodium gets pumped out of the ascending limb. That makes a salty interstitial fluid. Well, water leaves the descending limb because it's going to the area of higher salt concentration. The end result is that the filtrate first becomes saltier by losing water, and then less salty by losing the salt. And so it ends up quite dilute in terms of the filtrate, ends up being quite dilute because it loses all this salt. But because the salt is pumped out of the filtrate, we get this kind of multiplication in terms of, even though we have water coming out of the filtrate in the descending limb, we have salt coming back out into the interstitial fluid out of the ascending limb, and so that creates this really, really large gradient in terms of the interstitial fluid of the medulla. And we want to keep this. We do not want to lose this gradient. And so then we have the exchanger, the Vasorecta. The Vasorecta is permeable to both water and salt. And so we get this kind of equal opportunity exchange of salt and water between the blood and the interstitial fluid. And so the blood itself is osmotic, isoosmotic, so it's the same concentration as the surrounding interstitial fluid, and so it's very freely able to reabsorb water and solutes, kind of without messing that exchange of salt and water that is done by the loops of Henle. It prevents the salt that creates that gradient from being kind of just sucked out of the interstitial fluid. That gets rid of our gradient, and helps get rid of the water that was reabsorbed by the descending limb by allowing it to go into the blood. That again helps keep our gradient. So if we look, we're getting sodium and water, exchanges of sodium and water pretty equally. But if we look at the osmolality of the blood, you'll see it's pretty similar to the surrounding interstitial fluid. So in here we have sodium being reabsorbed by the blood, water being let out. Here we have sodium being released from the blood into the interstitial fluid and water being reabsorbed by the blood. And it basically just does this on a one-to-one basis, so that initial gradient where the ascending limb actively pumped out the salt and the water kind of followed the salt, we're getting all of that kind of water reabsorbed and the salt kind of maintained in the interstitial fluid, just so that we don't screw up this gradient right here. And now that we have a gradient, the collecting ducts can kind of use that to change the concentration, the osmolality of our urine. So if you were sitting inside one day, just watching some TV and drinking, copious amounts of water, then your hypothalamus is going to sense that you are quite well hydrated and will not release any ADH to the posterior pituitary, and the posterior pituitary won't release the ADH. Well, if you are drinking copious amounts of water, the osmolality or concentration of all your extracellular fluids basically goes down. You're diluting out your body fluids because you're essentially saying you're providing so much water to your body. That prevents ADH from being released by the posterior pituitary and decreases the amount of aquaporins, water channels, that we find in the collecting ducts, which means we get less water being reabsorbed by the collecting ducts, so more water remaining in your urine, and you get this large volume of very pale yellow, very dilute urine. Now, if you were outside in Georgia and you forgot to drink some water, then you're going to get dehydrated. That loss of body water increases the concentration of your body fluids. That results in ADH being released from the posterior pituitary. That increases the number of aquaporins in the collecting ducts, and thanks to the very salty interstitial fluid, as the fluid in the filtrate flows through the collecting ducts, it is reabsorbed. It goes from the area of lower concentration to the area of higher concentration, and you end up with a very small volume of urine that is much more highly concentrated, so more dark yellow. And so by using this gradient that the loops of Henle created, we are able, with the help of some ADH, to kind of change the volume and concentration of our urine to maintain the osmolality of our bodily fluids.